Welcome to our series on radome and bumper testing, where we cover everything you need to know about radome testing and the usage of the powerful QAR50 tester. Now, we will focus on the hardware choices the instrument offers. Since there are only two options, this is going to be a rather short video. The first option I would like to start with is the verification set. So you can see some verification plates lying on my left-hand side. So these are, in contrast to the QAR plates, both for transmission and also reflection verification. So the values on these plates, they are accredited. So you can truly verify the measurement results of the instrument by using the verification plates. So they are coming in a bag, which is the QAR50 Z44. It's the first option. The second option, and actually the only hardware choice you have with the actual instrument, is the polarization. There's two polarizations available. There's vertical polarization and horizontal polarization. In the setup you see here on my left-hand side, vertical and horizontal make limited sense only because the instrument is in the C shape. So the polarization always refers to the U shape. There we have vertical polarization and horizontal polarization. You can see that on the slide here as well. The left-hand slide shows the KO2 variant, which is the vertical polarization, and the right-hand side shows the horizontal variant, which is the KO3 variant. So knowing about the instrument has two different kind of polarization, what is actually the effect? Therefore, I have put one sample into the instrument. So this is an RX plate with foam, which basically has zero transmission loss. And we have 4 strings in there. The strings represent the heating wires of the radome. So the question is, in which polarization do we see the heating wires and where does the radome or we not see them? So currently they are in this kind of polarization. So that means with the instrument configuration, we are expecting to see the wires in the imaging. Why is that so? So we can either align the wires co-polarized with the radar. So that means the wires have the same polarization as the radar. And they are acting as kind of antenna, and they are interfering or interacting with the signal and therefore absorbing a bit of energy, and we can see them in the plots that we are creating. If the wires are cross-polarized, we don't see them anymore because they basically have no effect on the signal. We can see that in the measurement results here. On the left-hand side, we have this nice co-polarization, and on the right-hand side, we have the cross-polarization. So that means what I just said, on the left-hand side, we can see the wires. On the right-hand side, we can't see the wires. There's a significant difference between both the images, and if there would be something wrong with the wires, with the polarization, or some delamination effects, we would be able to see that. Same goes for the reflectivity. So on the left-hand side, again, we have the co-polarized wires, and on the right-hand side, we have the cross-polarized wires. So on the left-hand side, we see the effect of the wires. On the right-hand side, we don't see the effect of the wires. Question, do we also see them with single spot transmission loss measurements? We can have a look here. So on that side, so transmission attenuation for the co-polarized setup, where we have the significant influence of the wires, 0.16 dB. Transmission attenuation for the cross-polarized orientation, where we have insignificant influence of the radome or of the wires, we can't see them. You can judge yourself whether this is already a significant difference, but from our point of view, this is still more or less within the measurement tolerance of the instrument. So I would not say that you can detect the wires or delamination effects with a single spot measurement.